In the last class, I talked about the delta function, right? In the last class, we talked about Dirac delta function. Dirac delta function. Right, so what was the Dirac delta function? We represent the delta function that's located at T naught. In this, the delta T minus T naught. Right? So I gave you the formal representation of the delta function and the informal way of thinking about the delta function. Actually, the informal way of thinking about the delta function is going to be very important in most of the applications, right? So you can think delta T minus T naught as an impulse located at T naught, or as a spike located at T naught, right? So you have something like this. This is your T axis, and delta T minus T naught is going to be the spike located at T naught. Okay, this is the function of delta T minus T naught, right? So in the formal construction, we constructed delta function as a limit of functions, right? And what is the integral of delta T minus T naught? If you integrate delta T minus T naught from minus infinity to infinity, we would get 1, right? Actually, you do not need minus infinity, right? So if you will start somewhere here, right? For example, if you integrate delta function from T naught minus epsilon, T naught is here, I would walk epsilon distance along this direction, right? So T naught minus epsilon is somewhere here. So if I integrate delta function from T naught minus epsilon to infinity, then I have to go through this spike, right? So if you go through that spike, your area would always be 1, right? So that means if I integrate the delta function from T naught minus epsilon to infinity, you would get 1. Okay, so you need to check whether your spike is going to belong to the region of your integration, right? In this case, I'm going to integrate this function from T naught minus epsilon to infinity. Then this spike belongs to my region of integration. So as a result of that, it would be 1, right? So for example, suppose you are going to start the integration at this point, T naught plus epsilon. What would happen if you integrate delta function from T naught plus epsilon to infinity? You would get 0, right? Because you are not going through spike, right? Okay. This is the first property of the delta function, right? If you go through the delta function, your integration is going to be equal to 1. Okay, and at this point, function is not defined, right? You cannot say what is the value of this delta function. You can only say what is the integral of that, right? For example, if I integrate this delta function from T naught minus epsilon to T naught plus epsilon. Actually, in this case, I'm not going from minus infinity to infinity. I'm going from T naught minus epsilon to T naught plus epsilon, right? So when I am walking from T naught minus epsilon to T naught plus epsilon, I have to go through this spike. Okay, that means integration is going to be equal to 1. Equal to 1, right? This is the basic property of the delta function, right? Right. Next, we discussed several properties of delta function. What was the property number 1? It is, suppose you have some function ft, right? If you integrate some function from minus infinity to infinity, delta t minus t naught dt, this is going to be equal to ft naught. Okay, that means you can find the function value at t naught. Okay, so this is the idea. You have some function ft, and you have t naught somewhere here, and you have delta t minus t naught. This is delta t minus t naught. That is this spike located at t naught, right? So if you multiply these two functions, what would happen? Only you would get a spike whose height is ft naught, right? Because when you are multiplying these two, this portion would disappear, this portion would disappear, right? So that is the reason why we are getting ft naught, right? So this is also important. In this case also, you do not need to integrate from minus infinity to infinity. Suppose you integrate this product from t naught minus epsilon to t naught plus epsilon. Again, you would get ft naught. Okay. So if you integrate only delta function, you would get 1. But now what you are going to get? You are going to get the function value at t naught, right? You have two functions, ft and delta t minus t naught. If you multiply them together and if you integrate, you would get the function value at t naught. Okay. Right. Any questions about this property? This was one of the most important properties of delta function, right? So we can extract function values by through this integration, right? Next, I talked about impulse train, right? So delta function is, if you consider delta function, you can see one impulse, right? So suppose I'm having more impulses, right? Impulse train is something like this. So this is the impulse located at delta 0. That means this is the delta t. And this is delta t minus t. Right? Like that, you are going to have spikes at t, 2t, 3t. Like that, you are going to have infinitely many spikes. Okay. Right. So how do you express this signal? This is the call this signal as xt. What is xt? Is going to be equal to summation k goes from 0 to infinity delta t minus kt. Okay, because if you plug k equals 0, you would get delta t. If you plug k equals 1, you would get delta t minus t, second spike. If you plug k equals 2, you would get the third spike. Like that, you would get all these spikes when you are moving k from 0 to infinity. Right? Okay. Then suppose you are going to multiply this the same function by this impulse train. Then what would happen? So suppose instead of multiplying this impulse train, you are multiplying a function only by this delta t. Then what would you get? Function value at 0. Right? Now you have impulse train, so you are getting function values at each of these points. So you would get f0, ft, f2t, f3t, like that. Okay. So what can I say about integral from minus infinity to infinity? Ft times xt. Xt is my impulse train. It is equal to f0 plus ft plus f2t plus like that. So that means I would get summation k goes from 0 to infinity fkt. Okay. So instead of multiplying by one impulse, I took impulse trend and I considered the integral. Right? Okay. Any questions so far? So the previous property that I mentioned is very important. Right? Then what was the property number 2 that we discussed? That is the Laplace transform of delta t minus t naught. Okay. How did I find the Laplace transform of this function? How did I find the Laplace transform of this function?
Exponential? No.
Yeah, we would get the exponential.
And it'd be like negative t naught or something?
Yeah, we applied the previous property that I mentioned, right? So what is the definition of the Laplace transform? That is the integral from 0 to infinity e to the delta t minus t naught e to the minus st dt. Okay. Now again, recall the first property that I mentioned. What was the property number 1? Laplace of t delta t minus t naught is equal to t naught. So integral of this function from 0 to infinity minus infinity to infinity dt is ft naught. This is the property that we discussed. Okay. Right. So I can apply the same property here, right? Instead of f, I have e to the minus st, right? So I have 0 to infinity e to the minus st delta t minus t naught dt. So if you multiply any function by delta t minus t naught, you would get the function value at t naught, right? So in this case, ft is e to the minus st. So if you evaluate this integral, you would get e to the minus st naught. Okay. So this is the Laplace transform of delta t minus t naught. This is property number 2. Laplace transform of delta t minus t naught is equal to e to the minus st naught. Right? Is it clear how I applied the first property to evaluate the Laplace transform of this function? Right? Because I have same kind of thing, but instead of ft, I have e to the minus st. Right? We know that based on this formula, I will get ft naught. Now I just need to plug t naught instead of t. Okay. Right. So what can you say about Laplace transform of delta t? How do you get delta t? If you plug t naught equals 0, you would get delta t, right? So what would be the Laplace of delta t? It's 1, right? Because if you plug t naught equals 1, you would get delta t here. Okay, this is the third property, right? And what was the fourth property? If you convolute any function of delta t, you would get the same function. Suppose you have a function ft and you are evaluating ft convolution delta t, you would get the same function ft, right? That is property number 4. Laplace transform of Laplace transform. You have ft convolution delta t, you would get ft. Okay. Any questions so far about the delta function? Those are the main things that we discussed. Okay. And then we discussed some examples related to Laplace transform of delta t, right? So let's do another example. Suppose I have a differential equation like this. Y dash plus y is equal to delta 2 times delta t minus 2 by 0 is equal to minus 1, right? Problem is to find yt. Okay, you have a differential equation and it involves delta function, right? So try to find yt. So what is the first step? So we have to find something in the time domain. So what is our usual trick? We are converting this differential equation to Laplace domain, and then first we will find the Laplace transform of y. Then we would take the inverse Laplace. Okay, take Laplace of yt as ys. Laplace of yt is equal to capital Ys. Okay, first try to apply Laplace transform to this differential equation and try to find ys. Okay, after you find ys, you just need to take the inverse Laplace. How do you find the Laplace transform of the derivative? There's a formula for that, right? But it's first step, you have the differential equation y dash plus y is equal to delta t minus 2. I would apply Laplace transform to both sides. Y dash plus y is equal to Laplace of delta t minus 2. Okay. So then by linearity, what is the Laplace transform of y dash plus y? It is the Laplace transform of y dash plus Laplace transform of y is equal to Laplace of delta t minus 2. What is the Laplace of delta t minus 2?
Negative 2s.
Yeah, because instead of t naught, I have 2, so I would get e to the negative 2s.
But you'll also put 2 in front, right?
Yeah, you can write s2 or 2s.
No, but I mean, you have a whole 2 on the
Oh, yeah,
bottom.
just 2 here, right? Yeah, I missed that. Yeah, thank you.
So,
Right. Now, what is the Laplace of y dash? It is equal to s by s minus y0. We derived this formula. Right? S by s minus y0. And what is the Laplace of y? That is ys. Is equal to 2 times e to the minus 2s. Okay? Can you try to subject ys? Let me know if you have any questions. What is ys?
2e to the minus 2s plus 1 over s plus 1.
Minus 1, right? Minus 1 y, because this is y0, y0.
Okay, yeah.
Yes. So
I missed my side.
ys times s plus 1 minus y0, that is plus 1, is equal to 2 times e to the minus 2s. So ys is equal to 2 times e to the minus 2s minus 1 divided by s plus 1. Right. This is ys. Now our target is to find yt, right? So my next step is to take the inverse Laplace transform of this. Right? I will erase this part. Right. Ys is equal to 2 times e to the minus 2s minus 1 divided by s plus 1. Okay. So now what is yt? Yt is the inverse Laplace transform of this function. 2 times e to the minus 2s minus 1 divided by s plus 1. Okay. Then I would decompose this function, right? So this is equal to Laplace inverse of 2 times e to the minus 2s divided by s plus 1 minus 1 divided by s plus 1. Okay. Right. Then I will apply the linearity. Okay. Because we know that inverse Laplace transform is a linear operator. Right. So what would I get? 2 times inverse Laplace of e to the minus 2s divided by s plus 1 minus inverse Laplace of 1 divided by s plus 1. Now the next problem is finding the inverse Laplace transforms of these two functions. Right? If I can find the inverse Laplace transforms of these two functions, then I am done. Okay? Right. For that, actually this one is easy. We know what is the inverse Laplace of 1 divided by s plus 1. The problematic part is this one. Right? You need second translation theorem. Okay? Right. So if you have something like this, we discussed some examples like this. If you see e to the minus 2s divided by s plus 1, what is our usual technique? We forget about e to the minus 2s and we consider 1 divided by s plus 1. Okay? Right. Let's think about that. Have you all written this down?
So the first part of it is 2e to the negative 2. Then it goes into the open parentheses of t plus 1. And then it's times u to t plus 1.
You would get ut plus 1. Let's check. This is s plus 1. So we know that Laplace of e to the at is equal to 1 divided by s minus a. Right? We know that one. Right? So what can you say about the inverse? First, we forget about this e to the minus 2s. Right? So what is the inverse Laplace transform of 1 divided by s plus 1? Actually, s plus 1 is s minus minus 1. Okay? S plus 1 is s minus minus 1. So what do you need to put here?
Plus 2s, or,
Minus 1.
yeah, it'll be,
Right. So the inverse Laplace transform of 1 divided by s plus 1 is going to be e to the minus t, ut. Okay? This is equal to 1 divided by s plus 1. Okay. Now, but I don't have 1 of s plus 1, right? So that means I know the inverse Laplace of this function, that is e to the minus t. Okay? E to the minus t ut. The problematic part is this, but it can also be handled, right? Because what has happened in the Laplace domain? In the Laplace domain, you can see the multiplication by an exponential. So what would happen in the time domain? Translation, right? So remember that idea, right? That is the second translation theorem. Translation in the time domain would result in multiplication by an exponential in the Laplace domain, and multiplication by an exponential in the time domain would result in translation in the Laplace domain, right? Now, in this case, you have multiplication by an exponential in the Laplace domain. So recall this formula. Laplace of ft minus a ut minus a is equal to e to the minus as fs. Okay, right. So instead of a, what would I have here? I have multiplied by e to the minus 2s. So what is my a? It's 2, right? So what can we say about the inverse Laplace of e to the minus 2s divided by s plus 1? I need to translate this function by 2 units, right? So I would get e to the minus t minus 2 u t minus 2. Okay. Is it clear? You just need to find what's your a. My a is 2. Negative sign is there. 2 and then. Right? So what is the inverse Laplace transform of this portion? That is 2 times e to the minus t minus 2 ut minus 2. Okay. Any questions? Because I have multiplication by e to the minus 2, so I translated my time domain function. This is my original time domain function. Instead of t, I plugged t minus 2. Okay. Any questions? I think second translation and first translation theorems are the trickiest theorems, right? And they are very useful in those kind of scenarios, right? Any questions about this step? Get here? Because I know the inverse Laplace of this one, and if I multiply by e to the minus 2s, everything would be translated by 2. Okay? Let's move into another one.
I'm a little confused. Where you have negative t minus 2,
Okay,
wouldn't it be negative 2t minus 2? I didn't come across a problem that looked like that where you would, I understand how you got the negative 2, but
yeah, so what is your original function? So I had 1 over s plus 1, right?
Yeah.
And inverse Laplace transform of this one is e to the minus t ut, right?
yeah.
So this is your ft, right?
Mhm.
And what is your a equals to 2, right? Because you are going to multiply this function by e to the minus 2s divided by s plus 1. So your a is equal to 2. Is that clear?
Because you got a negative.
Yeah.
Yeah.
Because what is the result? Ft minus a ut minus a is equal to e to the minus a's fs. So this is my e to the minus a's portion. So a is equal to, right?
Okay, so
So inverse is going to be ft minus a ut minus a. Ft is e to the minus t.
uh-huh.
What is ft minus a?
Two-
Replace ft is e to the minus t. Replace t by t minus a.
mhm.
So what is a is 2. So what is ft minus 2? E to the minus, replace t by t minus 2. Okay.
But you don't have the a on top? The a falls off on the negative t?
No, a would come here, right?
Yeah, it moves down, but
Yeah. Ft minus 2.
yeah, wouldn't you distribute it to the two, to the t and the negative 2, which would make it, it'd be 2t minus 2, because I got the 2 part, but wouldn't the t also be a 2?
No, t would not be multiplied by it because
Okay,
if t is e to the minus t, right?
yeah,
So according to this formula, you would have a is equal to, you would have if t minus 2, ut minus 2, right?
yeah,
If t is this function, right? So when you are writing ft minus 2, just replace, you are going to replace t by t minus 2. That's what you are doing.
yeah, that I got.
Yeah.
It's just, I'm trying to figure like the 2, because you had the 2 before, and then when you brought it over, I know that
You
you
are talking
get,
about this 2, it comes from linearity.
yeah, no, but I mean, on
This
the top
two.
part,
This
yeah,
2, yeah.
so, yeah, I was just trying to figure out,
It just comes to this point, right?
yeah,
If you have e to the minus 2t, then you get 2 here, right? But here e to the minus t.
okay,
So you are replacing t by t minus 2.
that's right, okay.
Okay. Right. So next I would apply the idea of Laplace transform to RC circuit. Right. Suppose you have a DC battery, right? This voltage is suppose 10 volt, and you have a resistor, whose resistance is 5 ohms, and you have a capacitor, whose capacitance is 8 farads. Okay, this is the capacitance. This is the capacitance. This is the resistance. This is the voltage of your battery. It's a DC voltage supply, right? Okay. Initially, capacitor is not charged. So initial charge on this capacitor is 0. Initially, capacitor is not charged. Not charged. That means I represent charge by Q. Q0 is equal to 0. Initial charge on this capacitor is 0, right? Suppose there's a switch somewhere here. Suppose there's a switch, right? So initially capacitor is not charged, right? At t equals 0, I'm turning on this switch. At t equals 0, I'm turning on this switch, right? At t equals 0, switch is turned on. Okay? Because I'm going to turn on this switch. At t equals 0, then what would happen? Then the circuit would be closed, right? Then current starts to flow through the circuit. Okay, current starts to flow through the circuit. As a result of that, what would happen to the capacitor? It starts to get charged, right? So initially it does not have any charge, and when I switch on, current is going through the circuit. As a result of that, capacitor is getting started to charge, right? Okay. Now, first we would obtain a differential equation for the charge on this capacitor. That is, I need to obtain a differential equation that involves Q. Okay. Right. How do I get that equation? First, we will apply Kirchhoff's voltage law. By KVL, what I can say? This is my voltage source. This is the voltage across the resistor VR, and this is the voltage across the capacitor VC. Okay? By the Kirchhoff's voltage law, I can say 10 minus VR minus VC is equal to 0. Right? Right. What is VR? VR is equal to I times R. The voltage drop across the resistance is current times the resistance. Minus IR minus VC. What is VC? Remember this formula, right? Q equals CV. Okay? The charge on the capacitor is going to be equal to capacitance times voltage. So what is the voltage? You can write down the voltage across the capacitor by dividing charge by the capacitance. Okay? So what is that? QT divided by C is equal to 0. Right? Okay, now what is current? Current is the rate of change of charge. Okay, so instead of I would write dq over dt. Okay, so 10 minus R times dq over dt minus, instead of qt you can write q, right? Because we know that it would depend on time. So 0. Okay. Now I have the values of R and C. I would plug them. R equals 5 and C equals 8. 10 minus 5 dq over dt minus q divided by C. C is 8 is equal to 0. Okay. Right. Can I replace this 8? Shall I replace this 8 by another value? Then it is easy to simplify, right? I would replace this 8 by 1/2 farad, that is 0.5 farad. Then instead of C, I would write 1/2. Right, so what would I have? 10 minus 5 dq over dt minus 2q is equal to 0. Okay. Right. Now, what is the next step? My target is to find the find the charge on this capacitor. That means my target is to find QT. Okay. So how do you find? First, you find the Laplace transform of Q. Right. So take Laplace transform of Q as capital Q. Right. And first try to find Laplace transform, then apply inverse Laplace transform. Right. Okay. Can you try to apply Laplace transform to this equation? Take the Laplace transform of Qt as capital Qs. Initial charge is 0, right? You would need this one when you apply the Laplace transform, right? That's what is the Laplace of derivative. It is s times y, s times qs minus q0, right? Q0 equals 0. So I have this equation, right? 10 minus 5 times d cube over dt minus 2 times q is equal to 0. I would apply the Laplace transform to both sides. So what would I have on the left hand side? I have Laplace transform of 10 or 10 times Laplace transform of 1 minus 5 times Laplace transform of d cube over dt minus 2 times Laplace of q is equal to 0. Okay, right. Laplace of 1 is equal to 1 over s, right? So I would give 10 divided by s minus 5 times Laplace of d cube over dt, that is s times qs minus simple q0 minus 2 times qs is equal to 0. So what would I get? 10 divided by s minus 5 times sqs, and q0 is equal to 0. This is equal to 0. So I would not get this term. Minus 2 times qs is equal to 0. Right? So what would I get? Qs times 5s plus 2. I would get 10 divided by s is equal to qs times 5s plus 2. I'm taking these two terms to my right hand side. Right? So what is qs? Qs is equal to 10 divided by s times 5s plus 2. Okay. Right. Now I know the Laplace transform of qt. Right? So how can I find the inverse Laplace transform of this function? You can use partial fraction decomposition. Try to use partial fraction decomposition. So we'll try to find the partial fractions. And divided by s times 5s plus 2 is equal to a divided by s plus b divided by 5s plus 2, because I have two linear factors. So I can decompose this rational function in this way. Right? So what would I get? 10 equals a times 5s plus 2 plus capital B times s. Okay. Then we can plug values or compare coefficients. Let's plug s equals 0. If I plug s equals 0, what would I get? 10 equals to a, and that would give me a equals 5. Okay. Then I would compare coefficients of s. Right? What is the coefficient of s on my left hand side? I don't have any s terms, so 0. What are the coefficients of s in my right hand side? I have 5 times a plus b. Right? I have 5 times a plus b. Okay. So a equals 5. So what is the value of b? B is minus 5a. Is equal to minus 25. Okay. Right. Now I know the values of a and b. Right. So again, let's move into QS. So what was my QS? QS is equal to 10 divided by s times 5s plus 2. But now I can write this rational function as a summation of these two functions. So I would get 5 divided by s minus 25 divided by 5s plus 2. Okay, this is my QS. Or this is the Laplace transform of charge on this capacitor at time t. Okay, right. Then next time, this 5 is a problem, right? So from the denominator of this fraction, I'm going to take 5 out. So then what would I get? 5 divided by s minus 25. If I get 5 out, what would I get? S plus 2 divided by 5. Okay. Right. Now I'm in a good position, right? 25 divided by 5 would become 5. So what is QS? QS is equal to 5 divided by S minus 5 divided by S plus 2 divided by 5. Okay. This is the Laplace transform of QT. Right. Now what is the next step? What would be the next step? Inverse Laplace transform, right? Okay, so what is QT? QT is the inverse Laplace transform of QS equal to inverse Laplace of 5 divided by S minus 5 divided by S plus 5 over 2. Okay. Again, by the linearity, this is equal to L inverse 5 times L inverse 1 over S minus 5 times L inverse 1 over S plus 5 over 2. Okay. Right. Now, what is the inverse Laplace transform of 1 over S? It's ut, right? What is the inverse Laplace of 1 over S plus 5 over 2? Again, recall this one. Laplace of e to the at is 1 divided by S minus a. So if I replace a by negative 5 divided by 2, what would I get? I would get s plus 5 over 2. Okay, so a should be negative 5 over 2. So the inverse Laplace of this one is e to the negative 5 over 2 t t. Okay. This is the charge on this capacitor at time t. So it is equal to 5 minus 5 times e to the minus 5 over 2 t ut. Yeah, multiplying by ut to represent that this is valid for only for t positive case, right? Right. Any questions about that? Like that, we can, this Laplace transform is going to be very important in those kind of practical applications. Right? Right. Now, if I ask a question like this, what is the charge on this capacitor when time goes to infinity? When time goes to infinity, what would happen to Qt?
Goes to 0, no, 1.
What would happen to this term when t goes to infinity? E to the minus infinity is 0, right? So this term go to infinity, so there's a minus sign, so e to the minus infinity. This would go to 0, so you would get 5. Right? Or you can apply final value theorem, right? That we discussed. Because I mentioned that when we are in most of the systems, we are interested in the case where time goes to infinity, right? At that case, if it is difficult to find Qt, we can apply that final value theorem also. But in this case, we found Qt, so we can see that when time moves on, Qt would become 5. That means this was our circuit. Right? Initially switch was open and I closed the switch and current started to flow, and initial charge on this capacitor is 0, right? So if the charge on this capacitor is 5 coulombs, then there is no current through this circuit, right? So that means when capacitor gets start to charge, voltage would build up across this capacitor. As a result of that, initially current is high, right? So when capacitor is getting charged, the current would decrease, right? So when it is charging more, the current would further decrease, right? Then there's one stage where the current becomes 0. At that stage, the charge on this capacitor is equal to 5 coulombs. That is the idea, right? So after capacitor is fully charged, there would not any current through this circuit in this case, right? That means this capacitor would charge up to 12. In this case, I gave, what was the voltage of the battery? 10 volt. Right? Any questions about that one? Right. Then I would show you another application that we have not come across during the first week, right? That is the spring mass system, right? It is another application of differential equations. Have you heard about the spring mass system? That if you have a spring, suppose you have a ceiling or something like this. you have a spring. This is the natural length of the spring, right? So you are going to attach some particle or object whose mass is m kilograms, right? This is the natural length of this spring. So if you attach an object like this, what would happen to this spring? It would be stretched. Okay. So this is t equals 0. What would happen? It would start to oscillate. Okay. I would call this distance as x, and this would depend on time, xt, right? That means this is called as equilibrium position, right? Equilibrium position, and this is some state at time t, right? So what is the velocity at, in this case, what is the velocity at this point? It's 0. Velocity of this mass is 0, and it's in this case x equals 0 and velocity is 0, right? X equals 0, x dot t equals 0. So at t equals 0, x0 equals 0, and velocity x dot 0 is also 0. I hope you are familiar with this dot notation. In physics, dot is used to represent the first derivative, and double dot is used to represent the second derivative, right? Are you familiar with this notation? That means initial position is 0, initial velocity is 0, right? So when this spring moves down, there's a tension on this spring, right? So I would mark the tension as T. I would mark the mass of this object as mg. Okay. Right. Okay. Now, what are the forces on this object? There's a tension and gravitational force. Right. Okay. Now, I'm going to apply F equals ma that derives as a result of Newton's second law, right? I hope you have seen F equals ma, right? Force equals mass times acceleration, right? So x is the position, x dot is the velocity. So what is the acceleration? It's x double dot, right? So next time I'm going to apply F equals ma downwards, right? Let's apply F equals ma. Let's apply F equals ma downwards. Okay. So what is the force that acts along this direction? It is mg minus t, because mg is along this direction, t is in the other direction. So the total force downwards is mg minus t. Okay. Mg minus t is equal to ma. So that is m times x double dot. This is the acceleration, right? X is the position at time t, x dot t is the velocity at time t, and x double dot t is the acceleration at time t. Okay. Now what is the tension? I think in Cal 2 you might have learned that. How do you express the external force on this spring? That is given by k times x, right? The spring constant times x. Okay. So T is equal to kx, where k is some constant. Kx equals mx double dot. And also in this case, I'm assuming that air resistance is 0. There's no air resistance on this object, right? If we insert air resistance, then this will become more complicated, right? Right. Any questions so far? So this is the differential equation that governs this physical system, right? Originally I had a physical system, and this differential equation describes this physical system. Okay? Right. Next, now my target is to find xt. Right? Let's try to apply Laplace transform to both sides. Okay? Now mg is a constant, k is a constant, m is a constant, right? So let's apply Laplace transform. Then what would I get by the linearity? Laplace of mg minus k times Laplace of x is equal to m times Laplace of x double dot. Okay, I would take Laplace of xt as capital XS. Okay. What is Laplace of mg? If you take mg out, you get Laplace of 1. It is 1 over s, right? So I would get mg divided by s minus k times Laplace of x, that is xs, right? Equals m times. Now you have the second derivative, right? So how do you find the Laplace of second derivative? It is s square ys minus s times sim square xs 0 minus y dash 0. But both of them are 0, right? Y0 equals 0, so x0, right? X dash 0. X0 equals 0, x dash 0 equals 0. Because initial position and initial velocity are 0. Right? So this would go to 0. This is 0. So what would I get? Mg divided by s minus k times xs is equal to m times s square times xs. Right. Any questions about this equation? Right. Now let's try to subject xs. First I would take this one to the other side. I have mg divided by s is equal to xs times, what would I get? M square plus k. Okay. Right. Any questions? M is positive constant, k is a positive constant, right? So what is xs? It is equal to mg divided by s times m times s square plus k. Okay. Right. What is the next step? Now I know the Laplace of xt. So next I need to take the inverse Laplace transform. For that, I need the partial fraction decomposition of this function, right? Let's try to find the partial fraction decomposition of this portion. G divided by S times M square plus K is equal to A divided by S plus Bs plus C divided by M square plus K, right? So in this case, there are no numbers. All of them are variables. Not variables, S is our Laplace variable, and all the others are some constants that we don't know, right? Okay, so what is mg? It is equal to A times M square plus K, simple K, right? K plus S times Bs plus C. Okay. If you plug S equals 0, you can directly find A, right? You plug S equals 0, you would get A equals mg divided by K, right? If you plug S equals 0, this portion would disappear and you get K times A is equal to mg, A is equal to mg divided by K, right? Then I would compare coefficients of S square. So what is the coefficient of S square on your left hand side? You don't have any coefficients, any S square terms. So you would get 0 equals m times A plus B, right? Times A plus B. So B is equal to minus MA is equal to minus M equals MA plus B. So B is equal to minus M times A is mg divided by K. So B is equal to minus M square G divided by K. Okay. What can you say about C? If you compare coefficients of S, C would be 0, right? Because what is the coefficient of S on your left hand side? It's 0. And the only S term that you have on your right hand side is CS. So C is 0. Right? Now I have the partial fraction decomposition. Right? Now A equals mg divided by K. Yeah. Answer is correct. So let's move on. Erase this portion. I would go back to XS, right? Now I have the decomposition of this function. Now what is XS? It is equal to A divided by S. What is A? Mg divided by K. Mg divided by K divided by S plus Bs. B is minus M square G divided by K. Bs divided by M times S square plus K. K should be simple, right? It is the spring constant. Right. Next, I would take M out of my denominator. Right? So what would I have? Mg divided by K divided by S minus M square G divided by K, and I would take M out of the denominator. I would get M here, S divided by S square plus K divided by M. Okay. Right. mg divided by k divided by s minus I have m square, I have m, so I get mg divided by k times s divided by s square plus I can write k of m in this way. Square root of k divided by m to the power 2. Okay. Right. This is my excess and it is in a nice form now. Right? Okay. Now what can you say about xt? Xt is the inverse Laplace transform of this function. Mg divided by k is a constant, mg divided by k is a constant. Right? So what would I get? Xt equals mg divided by k times inverse Laplace of 1 over s minus mg divided by k times inverse Laplace of s divided by s square plus the square root of k divided by m to the power 2. Right? Okay. Now, what is the inverse Laplace of 1 over s?
Cosine.
1 over s? This one?
Oh,
It's
1
ut.
over s is just.
Okay. Right. What is the inverse Laplace transform of this function? It is kind of s divided by s plus omega square. Right? S divided by s square plus omega square. That is cosine omega t, right? So what is the inverse Laplace of this one? Cosine. Instead of omega, I have k divided by m square root t. Right. So this is my final answer. Xt is equal to mg divided by k minus mg divided by k times cosine square root of k divided by m times t ut. It is very interesting example, right? So this is the formula for the position of the object that we attach to the spring, right? And this square root of k divided by m is called as the frequency of this oscillation. Right? We know that omega is 2 pi f, right? So if you divide this by 2 pi, you would get the frequency of oscillation. Right? That means when we attach some object to the spring, it starts to oscillate. Right? This corresponds to that frequency of the oscillation. Right? Okay, it's kind of hard example, right? These things are not in the lecture notes, but since I'm having time, I would like to focus on some applications of Laplace transform. That would be helpful to understand the basics of Laplace transforms as well as how to apply them in the real world, right? If I get some more time on tomorrow, I'll try to add air resistance to this problem. In this case, I assume that there's no air resistance, but in real world, there will always be the air resistance. So then this would become more complicated, right? Okay. So today we'll stop from here, right? We'll continue on tomorrow. And I'll upload the exam today and I'll send you all an email after I upload the exam.